When Charles Darwin published Origin of Species, the frontispiece of the seminal work in evolutionary biology included two quotes. One, as we mentioned in our previous episode, was taken from William Whewell's Bridgewater treatise on astronomy, asserting that God's agency in the universe included the creating of universal physical laws that governed the processes that gave rise to the various phenomena observed by scientists. The other was a passage taken from Francis Bacon's Advancement of Learning. It read, quote, "To conclude, therefore, let no man out of weak conceit of sobriety, or an ill-applied moderation, think or maintain that a man can search too far, or be too well studied in the book of God's Word, or in the book of God's works, divinity or philosophy, but rather let men endeavor in an endless progress or proficiency in both." End quote. In setting out this passage, Darwin was countering an argument that would surely be advanced against his new theory explaining the case and the cause of the diversity of species, namely that man shouldn't tread in realms clearly reserved for the divine alone. Darwin's invocation of Bacon was important ground to stake out. Bacon was, in many regards, the patron saint of British natural philosophy, the veritable wellspring of what it meant to do science, or, as he called it, experimental philosophy. By quoting Bacon, Darwin was, in effect, telling his readers that his work and the conclusions he reached because of it resided squarely in the Baconian tradition of induction. However, when The Origin of Species was published in 1859, a quarter century after the now famous voyage of the HMS Beagle, the question of what that tradition actually was a matter of significant debate. On one side were John Herschel and John Stuart Mill, who argued for a radical application of Bacon's supposedly bias-free methodology, while on the other was William Whewell, who argued for what he saw as the true extension of Bacon's ethos, one that acknowledged the role of non-inductive elements in investigation of the natural world. This debate, one that would begin in the late 1830s, would grow to encompass not only natural philosophy, but also moral philosophy and political economy as well. Mill and Whewell wrote back and forth in response to each other's ideas in their various works as the debate carried forth. And while Mill would prove to be the victor in the short term, a case can well be made that it would be Whewell's ideas that would prove to be a closer representation of the true nature of scientific inquiry. In this episode of the Scientific Odyssey, we'll look at the arguments made by both men in an effort to more fully understand several issues in modern philosophy of science. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 4, Science and Certainty. Episode 7, William Whewell, A Victorian Debate. As we set out on this final part of our present voyage, there are a couple of things I need to get out of the way. The first has to do with my notoriously bad pronunciation of things. Usually, I can be counted on to get the stuff in English more or less correct, but in this instance, I have once again whiffed and, well, I've whiffed rather badly. As you might have noticed from the introduction, for the last several episodes, I've been pronouncing William Whewell's name correctly. I made the mistake of going phonetic in pronunciation, and is kindly pointed out by one of our newest crew members, Avon McMaster of the Endless Knot podcast, which, by the way, I recommend very highly for those who like linguistics. that wasn't actually the way to go in this case. So, henceforth, it will not be Whewell, but Whewell. The second thing I want to do at the outset is to acknowledge my major source for this episode, which is Laura Snyder's Reforming Philosophy, a Victorian Debate. Snyder does an excellent job of laying out a presentation of the various positions of each of our major protagonists and providing a wealth of supporting material in the form of direct quotes and scholarly research. This episode will mostly be an attempt to summarize that work, as well as break down the various arguments in terms perhaps a bit more accessible to those who are not students of philosophy of science. As always, if there are errors in this, please understand that they lie entirely with your navigator and not with Dr. Snyder's work. Those seeking a fuller and more complete discussion of the topic, I would heartily recommend her books. Finally, the debate between Mill and Whewell was not limited to science, but ranged far afield into a broad discussion of how to reform British society to be more equitable and egalitarian. While those interested in political science and ethics will find these elements of the debate intriguing, dare I say, just absolutely fascinating, they will be largely neglected here, except in so much as they shed light on the scientific aspect of the discussion. I apologize for this only to a small degree, as I don't want to continue to take this podcast towards Dan Carlin territory of 6-hour episodes released once every 6 months. Okay, with the preliminaries out of the way, let's dive in, and the best way to do that, I think, is to jump into the Wayback Machine and talk about Sir Francis Bacon. When we discuss science, and specifically how one does science, a name that frequently comes up as to the originator of a quote-unquote scientific method is that of the Viscount of Albans, and one-time Lord Chancellor to King James I of England, Francis Bacon. While I think such an assignment is actually deeply flawed, as it neglects not only the contemporary contributions to doing science made by continental figures such as Galileo and Kepler, but, more importantly, those made by early figures such as Robert Grosseteste and Roger Bacon in England prior to the Great Mortality, not to mention the foundational work done in that area by a number of Islamic or Arabic hakim, such as Ibn Sina or Al-Hatham. It is, though, where our story needs to begin. In the early modern period, no figure so strongly advocates for what might be designated as an empirical position as being the basis for a fundamentally reformed way of conducting natural philosophy as does Francis Bacon. So radical would Bacon's approach be that after his work is sort of rediscovered after the restoration of the British monarchy in 1660, it will be given a new name, what is called experimental philosophy, by its adherents, most notably men like Boyle, Robert Hooke, and Isaac Newton. So who was Francis Bacon? Why did he break with previous practice? And what was the method of doing natural philosophy that he put forward? Biographically, Bacon's most famous or well-known role during his time was that of being a lawyer. Born in 1561 to a family of minor nobility, Bacon was an extraordinarily gifted intellectual, and he attended Cambridge at age 12, where he studied Latin and the typical medieval curriculum. It is said that while there, he actually met Queen Elizabeth I, who was so taken with his precocious nature that she took to calling him the young Lord Keeper. It may have been while at Cambridge that Bacon was exposed to the writing of his similarly named predecessor, Roger Bacon, and became convinced that there were significant issues with the traditional scholastic curriculum being taught, especially in the realm of natural philosophy. Following the completions of his studies there, he traveled for a time in Europe, learning everything he could about how things were done there before returning upon the death of his father. For the next decade or so, and my apologies here to those of you who enjoy the ins and outs of political intrigue, which for much of his life seems to have been Bacon's bread and butter, but I'm going to skim over most of this. Bacon entered the bar, worked as a lawyer, and as an on-again, off-again political figure. He was deeply involved in the various goings-on around the court of the Virgin Queen, sometimes to his favor and often not. But as he grew in experience and wisdom, Bacon figured out how to turn things more often to his advantage and land on his feet, and began to find his way to higher and more influential positions within the royal court. After Elizabeth I's death in 1601 under the care of the noted natural philosopher William Gilbert, Bacon became a favorite of King James VII of Scotland, now James I of the United Kingdom. This would lead to his rapid rise through various positions until he was named Lord Chancellor of the realm, a position that really has no direct parallel in modern democracies, but that might be thought of as sort of combining the functions of both a prime minister and a chief justice of a Supreme Court. In 1621, Bacon would fall from grace due to a combination of poor decision-making and palace machination of various rivals, after which he would retire from public life and devote himself to writing philosophical treatises until his death in 1626. The greatest of these works was titled Magna Insaturato, or The Great Restoration. Planned to be a 6-volume work, it was never completed as Bacon died before the last 2 books could be written. The second volume of the work, consisting of 2 parts, however, was published, if never quite finished, and was titled Novum Organum. The title is taken from Aristotle's earlier work, Organum, or The Instrument, and that book from Aristotle was his work on syllogistic and inductive logic. Bacon's goal, both with the entire series and the more focused work, or New Instrument, was to effect an overthrow of older scholastic and medieval modes of thought and investigation and replace them with a new, more accurate way of looking at the world. So let's talk about that a bit. First off, as we mentioned a moment ago, while a student at Cambridge, Bacon seems to have realized that there were significant problems with the institutions that persisted from the medieval times into his day. These issues were not limited to just information or to just the information being taught in the universities about things like natural philosophy, but also in how the church was being run, how the legal system worked, and how ideas were being evaluated for accuracy. As such, Bacon came to the conclusion over time that there needed to be a wholesale reevaluation of how individuals and organizations went about gathering information, evaluating that information, and then using that information to form conclusions and develop outcomes like laws, rational political policy, and an understanding about the relationships that govern the natural world. In his view, the paradigm that had grown up around the writings of Thomas Aquinas was no longer adequate to guide political, religious, legal, or philosophical institutions in a post-medieval world. He therefore set out to offer an alternative. The first step in this was to, in his words, cast off various quote-unquote idols that got in the way of seeing the world clearly. These 4 idols, those of the tribe, the cave, the market, and the theater, as he called them, served to bias thought through making man the measure of all things, through enshrining personal experience and thought, through loaded language and association, and through received systems of education and wisdom, respectively. Thus, the first step towards understanding the world as it really was, especially in the realm of natural philosophy, was to rid one of these idols, and thus begin any and all observations and investigations with a clean or blank slate. Now, before we go any further, let me make 2 comments. First, while Bacon writes about these idols in a framework of doing natural philosophy, it should be understood that he clearly thought that such a process or set of processes should be used universally across all regimes of thought and argument. Second, it is useful, I think, to understand a bit of context of where this all is coming from. Bacon is fully contemporary with the great debate about the Earth and, by extension, humanity's place in the cosmos. He would have been 9 when Brahe observed the new star in the constellation of Cassiopeia, an event historian of science David Wooten says is the true beginning of the scientific revolution. His professional career in many ways follows an arc similar to that of Galileo in terms of rise and fall. He dies just a few years before Kepler does. The great intellectual/philosophical debate of his time would have been whether the Earth moved. Interestingly, in some ways, like Galileo, he would have seen that debate not just through the scientific discussion, but through more ecclesial and political lenses as well. As such, while I think he would have been very familiar with the various scientific arguments, he would also have been keenly aware of the many points of debate that would have had little to do with physical evidence, and instead been built around philosophical edifices. As I read each of the idols, it seems to me to be pretty clear that there is an obvious corollary medieval philosophical position that would support a geocentric model that is not very evidence-based. For example, in the case of the idol of the tribe, which Bacon claimed to be rooted in man's desire to make everything about himself, one of the arguments for a geocentric universe was that humanity was God's special creation, and thus would have to be the center of that creation. Politically, that would allow the ruler of any particular empire to claim that not only was he the center of the empire, but actually he was in fact the center of the universe. This, Bacon saw, would be a profound bias against making any significant progress on resolving the scientific question. We know, additionally, that Bacon had contact, at least through friends, with Galileo, and thus would have understood the opposition the Tuscan natural philosopher would have faced first from the academic establishment and then later from the religious hierarchy. So what was Bacon's solution to all of this? Well, it was really a recommitment to empiricism, or, put another way, developing an understanding of the physical world through intentional, structured, and direct observation of physical phenomenon. With the biases hopefully eliminated, Bacon said that the natural philosopher would select a topic of interest and study it in great detail, setting up carefully controlled and monitored experiments when possible that demonstrated a phenomenon's behavior in a clear and unambiguous way. In this, Bacon was amplifying Aristotle's empiricism that focused on observing only what took place in nature around a person. The experimenter was to be careful to conduct his investigation in exacting ways and take detailed notes about both methods and results. These experimental investigations and data would provide the raw material for the next step of the process. Once these data had been gathered, they were, whenever possible, combined with other data regarding similar phenomena, whereupon the investigator then created what Bacon would call a natural history. In this process, the researcher created classifications of the various investigations and data based on the presence or absence of certain characteristics. Bacon's own example had to do with the various phenomena associated with heat. In this natural history, he lumped together phenomena that produce both heat and light, then those that produced heat but no light, and then those which produced light but no heat. In doing this, the investigator could clearly see both the similarities and the differences between phenomena with the goal of hopefully identifying various characteristics that gave rise to these differences. In the case of his natural history, Bacon noted that the sun produces both illumination and warmth, while the moon only produced the former of those qualities. The same could be said for any of the other planets. Thus, one might make the inference that the moon has more in common with the other planets than it does with the sun. Bacon said that it was from these various natural histories that an understanding of the physical relationships between natural phenomena would arise. One thing that should be noted here, as will become very important to our later discussion, is that Bacon profoundly de-emphasizes the role of hypothesis formation, at least early on in the process. While there is some legitimate debate as to whether Bacon thought that once a phenomena had gone through enough rounds of investigation, the formulation of hypotheses that would then be tested was appropriate, it was clear that he felt that no such activity should take place early on, as he believed that such hypotheses would be subject to the same idol-based biases he had been trying to eliminate. For a variety of reasons, though, Bacon's writings on these topics did little to garner support among the British natural philosophy or political communities until after his death. While Bacon's contemporary, and sometimes scientific rival, William Gilbert can be seen as being the first person to use methods similar to what Bacon was suggesting, it wouldn't be until the 1630s that the method would be taken up seriously by Sir Thomas Browne in his work Pseudoxia Epidemica, which sought to address various hoaxes, superstitions, and scientific errors of the mid-17th century. Only after the restoration of the British monarchy would his ideas be more fully embraced, most notably by the secretly practicing alchemist Robert Boyle, whose work The Skeptical Alchemist can be seen as a fully Baconian tome, and Isaac Newton, who enshrined the methods in his work Optics. Later, it would be the pneumatic chemists, with their investigations of various gases and their reactions, that would take up the Baconian banner in such a way that it would lead to the first chemical revolution in the late 18th century. We should also mention, as we close this section on Bacon's works, a couple of other things. First, contrary to what one might read, Bacon probably didn't come up with the idea of the scientific fact. While his philosophical writings were instrumental in bringing this idea into the discussion in England, he never actually uses the term and the idea together in his writing. That wouldn't be done until the work of Thomas Hobbes, who, as a young man, had served as Bacon's secretary. Additionally, it is clear that the idea and the use of the term had been circulating through the writings of various continental philosophers at about that same time. This leads us to our second point, and that is that while empiricism would become the dominant way of thinking in Britain, that would not be the case in the rest of Europe. Following the long divide between rationalism and empiricism that may have originated with Plato and Aristotle respectively, Europe's more Platonic roots were much more evident in how it would reimagine doing natural philosophy in the modern period. With Galileo and Kepler, there was a much stronger emphasis on the representation of natural phenomena in idealized form through mathematical laws, something Newton, by the way, clearly adopted in his Principia. More importantly, however, it was the work of Descartes, with its roots in the axiomatic deductive reasoning of mathematics, that would profoundly shape European scientific work for centuries, even after his formulation of mechanics would be superseded by Newton's three laws of motion and universal law of gravitation. Okay, with that very lengthy introduction now out of the way, we can get to the middle of the 19th century and wade into a debate over the doing of science in what was thought to be a new era. While the revival of Bacon's work in the mid-1600s had sparked the British version of what many have called the scientific revolution, by the turn of the 19th century, the energy generated during that period seems to have run out. As we've discussed in earlier episodes, by the time Whewell and his colleagues are meeting to discuss philosophy and science in the 1810s, there's a sense that much of the forward-looking work is being done in places that are not Britain. In fact, Britain's venerable scientific institutions have, in large part, been taken over by rich nobility, seeking another title to add to their long list of things that separate them from the commoners, and its universities are profoundly behind the times, both in terms of overall curriculum when it comes to the sciences and specific areas of practice, as was the case in failing to move beyond the mathematical approaches of Newton's long after they had been superseded by continental developments in the 18th century. Whewell, Babbage, and Herschel would work with a number of other individuals over time to effect significant change with regards to these deficiencies, including reforming the mathematics curriculum at Cambridge, establishing the British Association for the Advancement of Science, along with other more discipline-specific scientific societies, and, in time, adding specific academic tracks related to the sciences to the Oxbridge universities, finally following a trend that had been present at several of the dissenters' colleges for a number of years. Whewell would accomplish this at Cambridge after being appointed the Master of Trinity College, arguably the most prestigious academic post in the realm, in 1841, and using his influence in that position to create an honors degree and associated Tripos exam in the natural sciences shortly thereafter. It will be on this foundation that initiatives like the Cavendish Laboratory at Cambridge would be established that would, of course, be the site of so much of the incredible work done in the late 19th and early 20th centuries in atomic and particle physics and the mid-20th century in molecular biology. These, very clearly, are structural changes, and as important as they are, they only tell a part of the story. At least as important as these was, during the middle of the 19th century, an ongoing debate as to how science ought to be done. What was the proper method of doing science? This debate would be begun in a work by John Herschel, but it would be carried on through the pages of their various publications by Whewell and a figure we have yet to talk about, John Stuart Mill. Now, as the more philosophically inclined listeners surely know, I could do a many-part biographical series on Mill alone and his life and influences, but obviously we don't have the time for such a digression here, so let me just try to sum up and make a few observations. John Stuart Mill was, to put it kind of bluntly, an experiment of sorts. Perhaps one might call him a social experiment. Of course, he was much more than that, given all of the potential, value, and dignity he possessed as being just a human being. But for his father, James Mill, and his father's friend, Jeremy Bentham, he and his sister were ways to put into practice their ideas about how to best run a society. The elder Mill and Bentham, and I'm oversimplifying this for the sake of brevity, were proponents of a philosophical school of ethics known as Utilitarianism. While utilitarianism is a subclass of what is known as the broader school of consequentialist ethics, it is undoubtedly the best known of these, and it operates on the maxim that the right thing to do, the ethical thing if you will, is to do that which creates the greatest amount of good, however one wishes to define that term, for the greatest number of people. Mill and Bentham, especially the latter, wrote extensively on the best way to do this in society, and when Mill had children, he decided to try to raise them as paragons of utilitarian virtue. Young John Stuart had learned Greek by the age of 3 and Latin by age 5, and was translating works from those languages into English soon afterwards. His father had decided that through education he would create something like the perfect evangelist for the utilitarian ideas, and so J.S., as he was often called, was shielded from other children his age and put through this really rigorous curriculum of study by his father and Bentham. By age 12, he was studying Aristotle and scholastic thought in depth, and at age 14, he was writing on political economy from the school of thought associated with David Ricardo, whom we mentioned in our first episode on Whewell. And I have to take a moment here to reflect on Mill's life, what it must have been like. There's absolutely no question that he was a truly gifted thinker with a brilliant intellect, but the sort of rigorous, structured, and sheltered upbringing that went along with basically being the subject of a long experience had to be a tough way to grow up. There's a part of me that thinks that the whole thing sounds pretty cruel, actually. Did John Stuart actually ever get to be a kid? Was he ever allowed to just, play? Or did everything have to have, some purpose in line with utilitarian principle? Ironically, in being groomed to be the apostle for a system that advocated for the greatest good, which often meant happiness, for the greatest number anyway, one has to wonder, was J.S. really happy? The answer to this probably can be seen in a crisis of faith Mill suffered when he was 20. For him, the greatest good meant the most just. In other words, justice equated with goodness, at least while he was growing up. In his mind, the whole point of ethics was to produce a just society where all people were treated equally. At some point during his 20th year, he found himself asking whether, if he achieved that goal in some fashion, would he find happiness? When he realized that the answer was no, it sent him into a crisis. What this tells me is two things. First, it's hard to imagine that he was really all that happy up to that point, given the fundamental basis of the question. Second, the whole thing just sort of tells us that Mill thought happiness was really important. Justice without happiness was an empty promise. Over the course of the next several months, due to this crisis, Mill would contemplate suicide. He would remain in this disillusioned state for a certain period until he began reading the work of the Romantic poet William Wordsworth. In these poems and stories, he began to understand that the version of utilitarianism he'd been taught was efficient, but also it was sterile and lacked any sense of value for the aesthetic. Specifically, it was the lack of beauty that he saw when he compared his education with the work of the Romantic poet. Slowly, through a growing appreciation of this in Wordsworth's work, Mill was able to walk back from the edge and find that justice had to be balanced with compassion for one's fellow human being. This compassion, he found, could only be nurtured through the consideration of beauty as shared human experience. This shared sense of beauty and compassion would then lead one to experience joy, something more than mere happiness or satiation. It was in this, then, that Mill found purpose again to continue work to build a just society. Along with this reformed version of utilitarianism, Mill would find himself migrating from a perhaps somewhat more conservative political, economic, and moral stance to a decidedly liberal one, at least for his time, something that would lead him into politics as a member of Britain's more liberal Whig Party. From this place, he would advocate over his lifetime for the abolition of slavery and the extension of voting rights to all British citizens, including women. Like Whewell, he would become a powerful voice in Britain's public square, both on account of the popularity of his writings and due to the various positions, both political and academic, he would hold in his life. So this finally brings us to the great Victorian debate. The whole thing was kicked off by John Herschel's publication of a book titled A Preliminary Discourse on the Study of Natural Philosophy in 1830-1831 as part of Dionysius Lardner's Encyclopedia series. This work can be seen as an outgrowth of two things: Herschel's participation in the Cambridge Breakfast Club conversations about philosophy and the doing of science, and his work in astronomy, wherein he took over the cataloging of an enormous number of celestial objects from his father William, the discoverer of Uranus. In this work, Herschel saw himself as executing Bacon's method of creating natural histories through exhaustive systematic observations of various celestial objects. While amazingly successful in this regard, he would eventually publish the most extensive astronomical catalog of objects in both the northern and southern hemispheres. Herschel found that drawing conclusions from the data he and his father had collected was a tricky business. Nowhere was this more true than in trying to ascertain the nature of nebular objects. Were they vast collections of stars, seen from so far away that the light from all of the contributors blurred into a seemingly continuous object? Or were they actually associations of gas and dust that were much closer to the observer? History would show they were a little of both. This led Herschel to advocate for a sort of doubling down on the Baconian method. He asserted that while nature was governed by natural laws, these laws were often difficult to determine and even more difficult to represent mathematically, thus leading to errors in understanding. Therefore, what natural philosophers should do, remember, Whewell won't coin the term scientist for another 3 or so years while Herschel is in South Africa. Therefore, what should happen, what these natural philosophers should do, according to Herschel, is seek to gather more data and only make claims of having discovered such laws when those things are clearly and unambiguously shown to arise out of the empirical data. In Herschel's account, this was a completely inductive process, with no use of mathematical or deductive reasonings to arrive at the inferences. The goal, he felt, was for the natural philosopher to, through this process, seek to discover an explanation that would bring together the various observed phenomena. A couple of quick observations, lest these things be missed. First, when I read up on Herschel's work, it sort of struck me as odd as to how it became such a hugely influential document. Charles Darwin would later write that reading Herschel's preliminary discourse was a life-changing experience for him, and it created within him a quote-unquote burning zeal to continue his work. To me, it seemed like it was just a restatement of what Bacon had written in the Novum Organum, but then I realized that was due to my perspective, and I was sort of missing the point. In a sense, it was a restatement of Bacon, but one that was compelling and powerful due to Herschel's own biography and scientific achievement. I think it's a bit like those stories in the Jewish Bible or Old Testament where the people of Judah have strayed from the path of God, the one that He's laid out for them, until some prophet or king rediscovers the Torah that has been in the temple all along and been being read by a few priests in the ceremonies, but has not really been heard of outside of the temple. When the scrolls are brought out and read aloud to the people of God, they have this incredible response of desiring to return to old ways. So, similarly, I think Herschel's discourse reminds the errant scientific community in Britain from whence it came, so to speak. More than that, though, again like a prophet of old, he takes the British scientific community to task for what it has become. A bunch of parish priests and part-time lawyers who tinker around with empirical investigation, but who aren't really committed to the necessary, thorough, rigorous, and systematic methods needed to actually discover anything of real importance. In the case of Darwin, it's really a reminder that as a natural historian or naturalist, he can't just look at a few species and hope to arrive at any real knowledge of the underlying principles that might govern what's going on with those species. He has to look at many, many different species in many, many different environments very, very carefully. And once all of that extensive work has been done, then he can see if there are any underlying principles or laws that reveal themselves. The final thing I want to mention, something that will become important down the road a little ways, is that Herschel does break with Bacon on some key points. While it is difficult at times to fully know what Bacon's complete picture of experimental philosophy was going to be given the incomplete nature of his work, it does seem clear that Bacon had left room for non-inductive processes in the picture that he had been developing. While it isn't always clear what the nature or role of those processes was, one can make a good argument, I think, for Bacon recognizing that there were certain pre-existing assumptions that everyone worked with, as well as the need to mathematize things at some point in such a way that the mathematics could then be used to provide greater insight. Herschel, in the discourse, rejects this for the most part. For him, there is induction from empirical observation and little else. So that's the opening salvo, and like I said, it was enormously influential. It also spurred off some questions in Whewell's mind. By its 1830 publication, Whewell had become familiar with the writings of Immanuel Kant and was certainly aware of his idea of a priori concepts regarding to how we structure our experience of nature, things like causation, space, matter, etc. Kant claimed that these a priori concepts could be and had been confirmed through empirical observations and thus could be assumed in all scientific theorizing. For his part, Whewell found Kant's picture intriguing, even if he did think that Kant had gotten some things wrong, and thus Whewell felt that Herschel's picture was lacking in terms of describing both how science really was done and how it ought to be done. Now, at this point, one might think that Whewell would write a response or a review or something expressing the areas where he both agreed and disagreed with Herschel, but instead he does something I think is really brilliant. He decides to be empirical before moving forward, and so he decides really to study the historical development of various fields of science and movements within those fields to see if patterns emerged from that data, as it were. This decision likely grew out of the work he had done with Richard Jones on political economy, wherein the two of them, along with Babbage and Herschel, had studied various data sets from across the world to develop counter-arguments to the scholastic, deductively driven work of David Ricardo. All four men, but especially Jones, published excellently sourced rebuttals of Ricardo's work based on empirical data gathered from historical records of various economies, not only in Britain, but across Europe and Asia. So it was that Whewell realized that if he were to really consider Herschel's position, he needed to take a look at the historical record as best as possible and see how it was that science had been done both successfully and unsuccessfully. The outcome of this research was a work titled History of the Inductive Sciences from the Earliest to the Present Time, first published in 1837. According to some scholars, this was the first rigorous work in what would become the field of history of science. In other words, it was the first thing that did what this podcast is trying to do. 3 years later, Whewell then published The Philosophy of the Inductive Sciences, founded upon their history. In these two works, Whewell sets out his view of how science has been done and how it should be done in distinction to both Kant and Herschel. And one quick note here. While the first edition of these two works would be published in 1837 and 1840 respectively, Whewell, as was the custom of the time, would substantially revise and supplement the works in each successive edition, and so it's usually the versions published in the 1850s that are referenced, as they contain within them the most completely and clearly stated versions of his ideas, refined in response to the promptings of his critics, including both Herschel and, as we will see, John Stuart Mill. So, what was Whewell's picture of science as a process and a methodology? The first thing to talk about is what he called the quote-unquote fundamental antithesis of knowledge. This term represents what Whewell saw as the dual nature of how we come to understand the natural world, both through subjective or ideal means and through objective or empirical means. And when he says ideal here, what he means is really from the realm of ideas. As he would write, quote, "In every act of knowledge, there are two opposite elements, which we may call ideas and perceptions." End quote. In setting forth this antithesis, or, as might be characterized in more modern terms, this creative tension, Whewell is seeking to find a middle path between Kant and the European rationalists and their emphasis on deductive methodologies that downplay the role of empirical observation, and the hyper-empiricism that can be said to have begun with the writings of John Locke and which had been embraced by Herschel. In a sense, like so many things in life, it's a bit of a Goldilocks sort of approach, in that Whewell seems to want to avoid the extremes as he sees them. What's important to understand, however, is that while he does see some blending of the two, there is a clear sense in his writing that he also sees these two methods of gaining knowledge of the world as being in tension, even as they are thought to complement and inform each other. The successful science, he claimed, needed to use both ideas and perceptions to arrive at a complete picture of nature. To ignore the first was to collect data without either purpose or organizing structure, while to neglect the latter is to produce descriptions that often have little bearing in what is taking place in reality. His example in the first case is one we've mentioned previously, that of the discovery of the laws of planetary motion by Johannes Kepler. Tycho Brahe had accumulated mountains of data on the observed positions of Mars in the nighttime sky, and yet, without the proper theoretical framework, these data were irreducible to something that had any meaning. It would take several additional ideas, things like understanding that motion represented an object's travel through a thing called space, the rejection of a physical framework such as crystalline spheres to account for that motion, the idea that the Earth did not occupy a privileged position in the heavens, the acceptance that there might be other types of mathematical descriptions of orbits beyond that of the circle for both Earth and Mars, and etc., etc. And all of that would allow that enormous collection of Brahe's data to be reduced to a set of three elegant laws, expressible in mathematical form, to be discovered and expressed by Johannes Kepler. As for examples of the latter error, that of using ideas in substitution of data, can be found in any number of instrumentalist explanations of physical phenomena, from the use of a quote-unquote caloric fluid to describe heat transfer, and the invocation of phlogiston to account for a number of chemical processes involving heating, to the claiming of an electrostatic effluvium to, explain electric current and the like. In each of these cases, while there was observational data that needed to be accounted for, there was not observational evidence of the means of explanation. The idea here had taken precedence over the observations an empiricist approach would require in order to support them, at least in Whewell's view. What is striking here, if I may step out of the historical narrative for a moment, is that in modern theoretical physics, there is a robust debate, one might say, about the role of mathematical elegance and or beauty as a measure of a theoretical framework's accuracy. While a number of particle physicists and cosmologists will point to an idea, maybe, something like particles being made of tiny multidimensional strings, as the mathematical representations are called. Or there may be something known as supersymmetry that will allow us to account for several heretofore unexplained physical questions. They may, say that those ideas are elegant or are beautiful, and thus they're more likely to be true than some other explanation. In opposition to this, there are a growing number of voices that are really starting to push back on this, what could be seen as a very rationalist approach. These critics suggest that the quest for beauty or elegance may in fact be leading physics further away from the more accurate descriptions of nature, especially since there isn't any empirical evidence to support them, and sometimes no sense in which such evidence could be acquired. So, getting back to Whewell's description of science, let's talk about his fundamental ideas just a bit more. What these are things that are supplied by the mind in order to structure our experience. They do not arise out of our experience as an organizing principle like maybe the periodic table might or Bacon's natural histories do, but rather they already exist. As he wrote, quote, "not a consequence of experience, but a result of the particular constitution and activity of the mind, which is independent of all experience in its origin, though constantly combined with experience in its exercise." End quote. These are things like the concepts of space, time, matter, cause, resemblance, etc. Unlike Kant's a priori ideas or concepts, though, Whewell did not put a limit on the number of these, nor did he think that they had all been discovered. In modern cognitive science or psychology terms, these might be thought of as sort of phenomenological primitives. In keeping with his religious views in terms of natural theology, Whewell also said that human beings are created by God with these ideas in place in the mind in a sort of what might be thought of as self-consistent way. God had created the universe a certain way according to certain principles and natural laws, said Whewell, and thus he also created human beings in such a way that their minds would have the frameworks with which to understand that creation. As Dr. Laura Snyder writes, quote, "Consequently, the mind is an active participant in our attempts to gain knowledge of the world, not merely a passive recipient of sense data. Ideas such as space, time, cause, and resemblance provide a structure or form for the multitude of sensations we experience. The ideas provide a structure by expressing the general relations that exist between our sensations. Thus, the idea of space allows us to apprehend objects as having form, magnitude, and position." End quote. Out of this, there are a couple of things that can be seen. The first is the one that I think is most interesting, and indeed most important, and that is the idea of what is known as theory-ladenness of our observations. Francis Bacon had claimed that if human beings could eliminate their biases, they would be able to experience, i.e. observe, the natural world without any sort of filters. Whewell, however, makes it clear that even if Bacon's state of a truly bias-free observer could be achieved, human beings still would have specific frameworks sort of hard-coded, as it were, into their minds that serve to give structure and context to that experience. As an example, the physicist can only conceive of and understand motion from within his or her fundamental idea of space. The concept of theory or theory of space thus influences all of the observations of motion he or she will make. It will be built into the types of experiments that are developed and run, and it will be fundamentally woven into the models. The same is true for causation. If you think about it, can you imagine driving a car without having the fundamental idea that your actions in the driver's seat, with the various control mechanisms, are causal in their relationship to how the car subsequently behaves? As we mentioned in an earlier episode in the series where we described Hume's problem of induction with respect to a lack of observation of causation, it is almost impossible to move from simple enumerative induction, where we establish a relationship based on repeated correlation events, to a description of nature based on natural laws and principles without having Whewell's fundamental idea of cause or something a lot like it. To sort of further illustrate this, James Burke, in his series titled The Day the Universe Changed, gives an excellent example of how theory-laden nature of observations can be important. In his example, he talks about how, all the astronomical data about the motions of the planets that had been gathered over the millennia, and how in medieval Europe this data was seen to confirm the geocentric model of the universe. When any new piece of data was acquired, say the appearance of a comet or the falling of a meteorite to the Earth's surface, well, that data was always interpreted through the scholastic Aristotelian picture of the cosmos that had the Earth at its center, unmoving. The theory was the dominant paradigm, and so all of the observations were interpreted through that lens. That is, until Copernicus came along and showed that all of the observations can be used equally well to support another model, one with the sun at the center. In this new case, all of the observations, and it should be noted that they are exactly the same ones that have been used to support the geocentric model, are now reinterpreted in light of a new theory and thus become supportive of that new theory. And so it's not until the new star observations of Brahe and the orbits of the moons of Jupiter and phases of Venus by Galileo that the observational evidence begins to disadvantage some of the models, i.e. the Ptolemaic description of the solar system, and support others. And This whole thing is really the heart of Thomas Kuhn's model of scientific revolutions, a topic that we'll return to at some later date. One final observation on this topic before we move to the other point. When we did our three-part series on the history of philosophy of time, one of the things that was really clear was that for many of the philosophers who have been historically involved in that conversation, there has been an assumption that the thing that we call time that is associated with our perceptions and mental states, i.e., things like that there is a past, a present, and a future, and there is something passing that seems to separate events and occurrences, that's the same thing that scientists describe as a physical property of the universe in some way, the most modern version being an additional fourth dimensional equivalent to the three spatial dimensions we perceive. But what if this isn't the case? I mean, those sorts of things, those are theory-laden, right? What if what we call time psychologically is a very different thing than what we call time in the relativistic version of our description of the universe, i.e. space-time? How would such a picture change our attempts to incorporate time, whatever that might be, into our descriptions of the universe and our perceptions of it? As I hope this example shows, how we talk about time is very much a theory-laden thing, I think, and that in turn fundamentally shapes our framework, our paradigm in how we experience and examine it. Now, the second thing I want to draw out of this, and hopefully this will give our brains a chance to cool off here a little bit, because what we just did there was like really deep, right? Has to do with how this part of Whewell's picture is viewed by other historians and philosophers of science. For some, Whewell is just an evolution of Kant and the other German idealists. However, as we've mentioned, I think this is inaccurate for a number of reasons. Kant wants to say that his a priori concepts really are the truth, and that, any empirical observations that are made are merely necessary to confirm those more fundamental truths. Whewell rejects the subordinating of empirical observation completely, instead saying, as we mentioned, that the fundamental ideas give the framework with which to better understand that data so that natural laws and principles can be developed from them. For Whewell, the observational data is still the foundation upon which all scientific investigation is built. There are also additional differences in the ideas of the two men, but in the interest of moving on, let's leave it at the conclusion that while Whewell was clearly influenced in his development of a two-factor model, as it might be called, by Kant's writings, his fundamental ideas and Kant's a priori concepts come from very different places and serve very different roles. The other thread one will come across, one we mentioned in our final episode on the problem of induction, is the idea that Whewell's writings serve as the first of the non-inductivist approaches to understanding how science creates certain knowledge. The height of this movement will be found in the writings of the Austrian philosopher Karl Popper, who, along with others, develops what is known as a hypothetico-deductive model of doing science that does not truly rely, or does not really even rely on inductive methods to create that scientific knowledge. Here again, while there is certainly an argument to be made that Whewell's inclusion of fundamental ideas in the role of creative hypothesis formation and development is both an important step and very influential to this later description, it is clear that he would have rejected anything that would have downplayed or eliminated the role of empirically based induction. As we have noted, for Whewell, as supported by the historical evidence, science was a foundationally inductive process, and, as such, all of the knowledge it produced represented or rested on the processes of gathering data using the senses. In fact, when the criticisms of Popper and the what we call HDM or hypothetico-deductive method proponents are leveled against their claim that scientific knowledge is actually deductive in nature, many of these will sound as if they come straight from Whewell's writings. So how does this all manifest? For Whewell, there are really three major things or scientific processes that arise from his fundamental antithesis. The first of these he calls colligation. This is the process wherein a scientist takes several seemingly separate but possibly related facts and brings them together under one larger description. In the case of Kepler, he took the various observations of Mars' orbit made by Brahe that didn't seem to make sense either separately or in conjunction with older ideas and brought them into a single, coherent picture by giving both Mars and the Earth elliptical orbits through space, orbits wherein the speed of the planet varied depending on how close it was to the Sun. As can be seen, there's a lot of non-empirical, non-inductive stuff that Kepler had to have done to make colligation happen, and that's where both the fundamental ideas and the profoundly creative intuition come into play. Here, Whewell claims that Kepler had to use a process of non-inductive inference to arrive at these insights that would allow him to colligate Brahe's data in a way consistent with each other. What's more, Whewell will, in other parts of his writings, express the position that the inference of physical laws from data can come from a whole host of different types, including enumerative inference, eliminative inference, and analogical inference. This, of course, was a sharp break from the process as Herschel had seen and described it. Whewell would call it discoverer's induction, and it would be the thing that he would be most criticized for, and actually where he's probably most correct, at least in the humble opinion of this navigator. The second step of this discoverer's intuition was to extend the principle arrived at through colligation to other similar objects, phenomena, or classes of objects. For example, once Kepler comes up with the idea that Mars has to move in an ellipse around the Sun according to certain laws of motion, he then extends that idea to the other objects orbiting the Sun, namely Mercury, Venus, Jupiter, and Saturn. Additionally, he can apply it to the Moon's orbit around the Earth. This is then, finally, extended to all quote-unquote planets, meaning all objects that orbit the Sun, including things like comets. In this, Whewell is mirroring Bacon's assertion that science should progress in developing increasingly broad categories of generalization of physical laws, and in doing so will be able to account for possibly unobservable phenomena such as the orbits of asteroids, at least unobservable up to that point. Most recently, interestingly enough, in a sort of modern sense, there is a suspected large planet-like object thought to be orbiting the Sun in the outer reaches of our solar system in an area known as the Kuiper Belt. We certainly suspect that that object, and sort of the way we're inferring that that object might be there, is actually through the application of this sort of a process. One should note that this process in two steps was not thought of as one being merely guesswork by Whewell. His discoverer's induction was strongly guided, by observational data, the fundamental ideas, and an intuition developed through long experience with the types of problems and phenomena associated with the system being investigated. Kepler would not have been successful in his pursuit, claimed Whewell, had he not spent years working with and teaching mathematics, specifically the geometrical mathematics of conic sections. As our third and final sort of step, we sort of have to look at a three-piece part of that. Once a description of a system is developed, i.e. a hypothesis formed using this method, Whewell said that it had to be confirmed before it could be thought of as empirical truth. This confirmation process had three parts. The first might be called in modern terms prediction. As he wrote, quote, "Our hypothesis ought to foretell phenomena which have not yet been observed," end quote. The second is what is known as consilience, meaning that they should, quote, "explain and determine cases of a different kind from those which were contemplated in the formation," end quote, of those hypotheses. Finally, there was the criterion of coherence, or that hypotheses must, quote, "become more coherent," end quote, over time. The first confirmation criterion, I think, is pretty obvious. The hypothesis should be able to make predictions about the behavior of systems that are of the same kind as the ones that led to the formulation of the hypothesis, but that have not yet been observed. Thus, when William Herschel discovered Uranus and Leverrier Neptune, Kepler's laws of planetary motion had already predicted that their orbits would be ellipses. Confirmation of these predictions lent support to Kepler's laws. What Whewell saw as a much more important confirmational criterion was that of consilience, or that the hypothesis could explain the behavior of types of systems that had not been used in the development of the hypothesis. In his writings, he used two examples to illustrate this: Newton's universal law of gravitation and Dalton's atomic theory. In the first case, Newton had developed a universal law in order to explain the orbits of planets and that of the moon, basically as a way of explaining Kepler's laws of planetary motion. However, Newton very quickly realized that it could be used to account for a number of other phenomena, such as the causes of the tides, the shape of the Earth, other allowed orbital trajectories in addition to ellipses, etc. This is that sense where a hypothesis of about a single set of phenomena could be used to explain a whole other set of phenomena and thus exhibit that property of consilience. In the case of Dalton's model of the atom, it could explain conservation of mass in chemical reactions as well as both the laws of definite multiple portions, and thus it was sort of developed and useful in understanding chemical reactions. However, as time went on, it was shown that this model was able to account for various gas laws, thermodynamic principles, and Brownian motion, to name just a few extensions of the model in explaining other phenomena. Hypotheses that could be used to better understand a wider range of physical phenomena than had originally been envisioned were said by Whewell to be more likely to be vera causa, or true cause. Lastly, stemming from this idea of consilience was that of coherence, or the belief that as the hypothesis was applied to a greater number of cases, it would become more coherent. This would be seen with atomic theory after Whewell had died in the development of various forms of the periodic table and other advances made in chemistry over time. Conversely, Newton's universal law would see a peak in its coherence with the discovery of Neptune and then begin to fail in that respect, as astronomers attempted to explain the motions of the planet Mercury. Only once a superior hypothesis, that of general relativity, was proposed, would that problem be solved as a part of a process of confirmation for that new superseding idea or model. All of this led to a picture of science that Whewell saw as being able to produce necessary truths. These truths, however, were very different than what one might imagine. In a sense, if a scientific hypothesis was treated as an axiomatic statement, concurrent with whatever fundamental ideas form part of that hypothesis, then the things that could be derived from that hypothesis necessarily had to be true. If a hypothesis held to a flat description of space, for example, then two parallel straight lines in that space could never intersect. What is important to understand about this, however, is that a hypothesis might be held to be true at a given point, but as that hypothesis was inductively arrived at, it might change in order to become a more accurate description of what reality really was like. In this sense, Whewell viewed science as a progressive enterprise, wherein scientific activities progressed in moving away from a position or state of ignorance to one of more accurate knowledge as informed by ever more accurate and insightful empirical observation. The scientist might not know just how close they were to a quote-unquote absolutely correct description of nature, but he or she, with each iteration, would come up with a better or more accurate hypothesis, and thus the scientist could be said to have progressed away from a less correct one. All in all, this is a very compelling picture, and one might think that it would have met with broad acceptance, or at least with widespread praise for introducing new ideas that illuminated other aspects of scientific inquiry, especially given its basis in a historical examination of previous practitioners and their work. This was certainly the case with Charles Babbage, who saw Whewell's description as revelatory. Unfortunately, that wasn't the case for many others. Both John Herschel and Richard Jones were profoundly uncomfortable with Whewell's inclusion of non-inductive elements into the process, and both said so, both personally and in writing. Nevertheless, both men remained close friends with Whewell throughout their long disagreement with his description because of the respect they had for him as a scientist, as a historian, and as a philosopher. They could disagree with his ideas without disagreeing with him as a person because, in their minds, this was about reforming the way in which science was done, something that, while important to them, wasn't seen as a profoundly foundational issue, especially given Whewell's continuing reliance on empiricism and induction as the basis of his description. There were, however, others who were not so generous, most notably John Stuart Mill. As a result, over the course of more than 2 decades in many papers, books, book reviews, speeches, and the like, the two men would hold an ongoing debate that would eventually touch on nearly every aspect of British public life. So, to understand Mill's beef with Whewell, we need to broaden things out a bit. As we said when we introduced Mill, he had emerged from his, for lack of a better term, crisis of faith with a reformed version of utilitarianism, one that was very much in line with political liberalism in Britain at the time. Political liberalism advocated for a vast expansion of rights for the various oppressed and underrepresented groups in the British political and socio-economic system in ways similar to the New Deal and Great Society programs in the United States in the 1930s and 60s respectively. The fundamental tenet was that all human beings were entitled to the same rights and opportunities regardless of their state or class in British society, and that all obstacles to such reforms should be removed. In opposition to this, on the conservative side of the spectrum, were a number of individuals who argued from the position that there was a particular ordering of society that was proper, one that had been handed down from earlier generations and that should not be changed. People had their places in society, and those places were, in a sense, ordained by something greater than themselves, i.e., natural law or God's divine providence. To deviate from these time-honored traditions was to invite disaster and anarchy, as had been the case during the French Revolution, or later, the revolutions of 1848. Proponents of these positions would often state justification for their positions as sort of assumed truth, and then deductively work out their conclusions from those. Conclusions, of course, that almost always seem to entrench people in their quote-unquote stations, which enshrine the social and economic inequalities already present. It was profoundly scholastic in a sense, and often borrowed from the very arguments made by those same medieval scholars. For a liberal agnostic like Mill, this was maddening. All around him he saw a lack of justice, profound suffering, and deep disenfranchisement based in inequality, and it both broke his heart and turned his stomach. More importantly, though, it violated his deeply held utilitarian moral principles. And this is where I want to take just a moment to break out of our information-driven narrative for a moment and just better understand what's about to take place. From my perspective, I've tried to see how Mill would have imagined all of this as a youngish man. He's been raised as a science experiment by his father and Jeremy Bentham. His childhood and early education was really a never-ending series of ever more rigorous intellectual exercises designed to mold him into some sort of moral philosophy warrior for utilitarianism, where the only thing that mattered was what deductively flowed from certain philosophical axioms. He's done all the work and read all the great books and thought all the great thoughts, and at some point what he realizes that it's all just some kind of a unyielding crystalline artifice that doesn't bring him any joy. Instead, his rigid adherence to all of these logically received truths has made him miserable enough to want to take his own life. Instead, what rescues him is romantic literature and its claim that there is more to the human experience than just unforgiving and unchanging natural laws and greater industrialization. People there aren't seen as cogs in some vast manufacturing machine, but as fellow travelers through this thing called life. A voyage made immeasurably better when we all have compassion for each other. Something engendered by our shared aesthetic experience, our mutual appreciation for those things that are beautiful. As Mill looked around, what he saw was a Britain going in the wrong direction. One that would inevitably result in his mind in a popular revolution as more and more people got crushed underneath the wheels of economic change and social dislocation. He saw a time coming when, if the inequalities weren't addressed, the disenfranchised would rise up and take what they felt should be theirs by force. Even though Britain had a parliament which was supposed to represent the will of the governed, it was becoming clear to more and more people that in many places, known as rotten boroughs, the local aristocracy had co-opted the electoral process, thus denying them a say in what the laws that affected them were, those that were directly enshrined. By the way, does any of this sound familiar in our contemporary political dialogue? So what Mill wanted to do was to reform socioeconomic and political systems to be more along the lines of liberal party solutions. The problem was that he and his fellow party members continually ran into these sort of axiomatic, deductive, dogmatic arguments about how, things were supposed to be the way they were because that's the way they were supposed to be. That's the way they were meant to be. These arguments went something like, certain people were going to be aristocracy, and they should have political power, and other people were always going to be poor, and that was their lot in life, and they shouldn't have political power. Men were the only ones who were allowed to vote because they were the only ones who had the proper faculties, whatever those were, to be able to understand the issues, while women weren't suited to such activities and thus should remain at home. Europeans were racially superior to other people and thus had both the right and responsibility to both enslave those other peoples and impose their cultures and values upon them. And these were the sorts of arguments that were made up over and over and over again in so many different forms. And I can imagine that they burned Mill up. So what did he do? Well, he decided, a bit like Bacon and Galileo had a couple of centuries earlier in the sciences, to say that deductively arrived at knowledge was subject to profound bias and thus deeply suspect. Instead, the only reliable knowledge in human experience was that arrived at by inductive means. Now, to give you a sense of just how far he's willing to go with this, let's consider mathematics for a minute. Mathematics, something that was an important part of the British intellectual identity going back to the Oxford calculators and Isaac Newton, is an entirely deductive enterprise, as we've mentioned before. But Mill can't have anything that produces useful truths actually be deductive, because once he allows that to be the case in one instance, he feels like his opponents will have an opening to claim that all sorts of other areas of inquiry, including moral philosophy, can also be decided by deductive means. So what he claims, and he writes quite extensively on this, is that mathematics is not, in fact, deductive at all, but rather a completely inductive process. As you can imagine, if he's willing to go that far in his thinking, his views on the proper way to do science will be even more radically inductive. In a sense, I get where he's coming from. Every time someone in his liberal circles proposed a reform they think they can show will help British society become more fair, equitable, and just, using some form of inductively arrived at evidence, there's an old aristocratic dude or his lackey who's going to stand up and shout down the idea on the basis of some argument rooted in deductively arrived at moral law. Again, I don't think it takes too much thought to see similar sorts of things going on, by the way, in our political arguments today. Think about how frustrated you get when you know that all of the evidence and scientific consensus around the human effects on climate change and what policies might be beneficial in alleviating those effects. And then you hear some political shill for, the fossil fuels industry or somebody like that stand up in a legislative body and begin to spew forth ideas and arguments for which there is no actual empirical evidence. I really get Mill's frustration. I think probably many of you do too. And this is where he's going to get crosswise with Whewell. The whole fundamental antithesis thing is a step in absolutely the wrong direction for Mill. Bringing in non-inductive elements is just opening the door for these guys, and yes, they're always guys back then, to now bring up some version of some sort of fundamental idea that would allow them to paint whatever scientific veneer on their patently unjust or inequitable positions they wanted to advance in the public square. And not to beat a dead horse here, but again, does any of this really sound familiar, right? For Mill, science has to be inductive, and fully so. The problem is that he has to develop a way to do some of the things that Whewell's model does so well, like produce truth or some reasonable approximation of it, and, more important, come up with a process of inference that will lead to the extension of knowledge beyond that of direct observation. In his seminal work on this, titled System of Logic, Mill sets out to do this by developing 5 different quote-unquote methods, as he calls them, including things like agreement, difference, the method of residues, etc. He then goes on to specifically attack Whewell's example of Kepler as an exemplar of the process that Whewell had advocated by saying alternatively that Kepler was little more than just being lucky in his discovery, and that his discovery was really not all that special and almost anybody could have made it. In historical perspective, both arguments are riddled with problems and inconsistencies that arise primarily from Mill's lack of knowledge about the history of science and any real experience as a practicing scientist. What really does seem to be the case, rather ironically I add, is that his ideological need to exclude any form of knowledge creation other than induction is driving much of his thinking in this area, as opposed to using empirically based knowledge of how science has been done successfully in the past. The debate is driven, however, by a more personal consideration than this. Whewell and Mill came from very different backgrounds, and as the debate began, their ages were different enough that there was almost certainly some generational dynamics going on in how they saw things, and how they saw things differently. As we said, Whewell was a pretty conservative guy when it came to values. This doesn't mean that he was a member or supporter of the Conservative Party in Britain, known as the Tories, but rather that he tended to view the world through a religiously influenced, traditional values sort of lens. He was, for lack of a better term, what we might call a small c conservative, who tended, especially later in life, to side with things being the same today as they were yesterday, at least until they could be shown that something else would work better. Mill, on the other hand, was an agnostic who saw Britain as being fundamentally broken in many respects, and who seemed to feel that men like Whewell were standing in the way of true progress, almost as much as those who were making the arguments against change. In other words, Mill was a bit of a zealot who saw things in an us versus them way, at least in the political and what we might call moral philosophy arena. What didn't help any of this was that Whewell also developed a system of moral philosophy that was very similar to his understanding of scientific inquiry, in that he said that there were absolute moral truths that could be known and applied through a set, again, of fundamental ideas, this time being things like benevolence, justice, truth, etc. These, he said, would lead to self-evident moral truths/laws that could be accessed through the use of reason. And this all starts to sound pretty deductive. And so this, to Mill, seemed to be a blatant justification of the sorts of arguments being made by his political opponents, and so he was led to more stridently argue against Whewell's position. The truth, however, was that Whewell, while he claimed that there were self-evident truths, just as there were absolute physical laws, didn't claim that humanity had arrived at them yet. Just as we were still trying to get a better understanding of the fundamental ideas in the physical realm through investigation and observation, so too did humanity have a ways to go to really understand the fundamental ideas in the moral realm. Additionally, Whewell explicitly rejected the idea that any single person could claim to intuit these more moral ideas, saying rather that such knowledge was the product of a culture or society and its collective activity in terms of public discourse and representative democracy. The two men would argue through the pages of their work for over 2 decades, with Mill often unfairly or harshly portraying Whewell's work, and Whewell condescending to Mill. In Mill's case, he just couldn't do what Herschel and Jones had done and recognize Whewell as an honest, forthright, and good man dedicated to moving away from ignorance towards better knowledge through healthy investigation. For years he would see, and unfortunately treat, Whewell like some sort of caricature of an academic blowhard, a posture that was deeply offensive and hurtful to the older man. In response, Whewell often referred to engaged Mill or his ideas in the public square in a way that treated the young man as an equal, as was his due. As such, the two men, in spite of the urging of their friends, would never meet in person, something that would likely have gone a long ways to bridging the gap between them. Late in Whewell's life, however, Mill would come to recognize his error. The issue would be that of Britain's position on the question of slavery in the United States. Mill had railed against the tacit approval the government had shown the southern states by continuing to trade in the cotton produced by slave labor, and he assumed wrongly that Whewell supported the government's position. when the older man wrote a strongly worded position paper saying, in essence, that the government's actions gave lie to Britain's own abolition of slavery throughout its empire in 1833, Mill realized that he had long been wrong about Whewell. In response, he wrote a letter to Whewell, thanking him for what he had written, expressing his gratitude in knowing that a person of such great reputation had agreed with him, and tacitly apologizing for his earlier attacks on Whewell's character. While the two would never agree on how science should be done, or on how knowledge was arrived at, the letter marked a cessation of hostilities between the two men and a détente of sorts in the great Victorian debate they had conducted over the years. As we close both this episode and the series, allow me to make a few more biographical remarks about Whewell. The great man would hold 3 positions at Trinity College in addition to being a fellow there. He was, as we've mentioned, professor of mineralogy from 1828 to 1832, professor of moral philosophy from 1838 to 1855, and master of Trinity College from 1841 until his death in 1866. He would marry twice, and both his wives would precede him in death. He would have no children. As mentioned earlier, while master at Trinity, he would oversee a number of reforms in the natural sciences that set Cambridge on the path to becoming one of the finest institutions in the world when it comes to those topics. He died on March 6, 1866, a few days after suffering a heavy fall from his horse. In his will, he used his wealth, acquired from years of somewhat frugal living and the sales of his contribution to the Bridgewater treatises, to create a professorship in international law at Trinity College, as well as a number of student scholarships for the study of the same, as a way to establish, quote, such measures as may tend to diminish the causes of war, and finally to extinguish war between nations, end quote. In spite of his remarkable life, one that it has taken us 3 episodes to just merely overview, William Whewell is little more than a footnote in most places. Why is this? I might offer a few reasons. First, he never had what one might call a great breakthrough discovery in the field, or in a field that had society-wide impact. While his work in science, in the fields of geology, tidology, and other areas, is certainly excellent, it never produced a paradigm-altering discovery. While I think his work in the history and philosophy does rise to that level, these fields are broadly consigned to the realms of esoterica, even to scientists and historians. Moreover, only recently has his work in these fields been recognized as being truly revolutionary as it was. Second, Whewell, unfortunately, had a tough draw in terms of the men he was debating against in that great Victorian debate, the reason that I think his ideas were neglected for so long. Against him on one side was his good friend John Herschel, who was, well, about as close to British scientific nobility as one can imagine. Not only were Herschel's investigations in astronomy profoundly significant, his work in the early development of photography, in large part, made that technology actually possible. On the other side, of course, was John Stuart Mill, a brilliant philosopher and communicator. While Mill's arguments I think, be rightly seen as being inferior and at times just flat out wrong, he was on the right side of history in what he was advocating for in terms of his liberal politics. Almost every one of Mill's political positions are now taken for granted as fundamental to liberal societies across the globe. While Mill wasn't right about science, he was right enough about a lot of the other really important things that his voice in the scientific debate also tended to carry the day. Third and finally, Whewell was, without a doubt, one of the truly important public intellectuals of his day. The thing is that society has traditionally been very quick to forget those individuals after their voice is silenced, and their views, and this I think is the important thing, their views are incorporated into the broader cultural conversation. There's no question that he was seen as remarkable during his time and shortly after his death. They put up a statue of him next to Newton and Bacon, after all. But as the broader culture moved on, he became a man honored only in his own place. One wonders how long it will be before men such as Paul Allen, who had such an important impact through his work in founding and leading Microsoft, or Larry Ellison at Oracle, will disappear into the shadows of men like Steve Jobs and Bill Gates, only to be remembered in museums of science and technology or at industry conferences. Once the profound ideas of such men are absorbed into the broader cultural context, they're often forgotten. Nevertheless, even if he is mostly forgotten to the broader culture, it is clear, I hope, that William Whewell was and remains a man of important consequence. Our understanding of how science is done, both historically and in the present, would not be possible without his work and insight, and his ideas will have a profound impact and a profound effect on our sort of understanding of those processes starting in the 1960s and moving forward. And so it is that we, too, leave his life and the issues he worked on for a time at least. This episode, as I've said, wraps up our short Season 4 and its consideration of the problem of induction and the individuals who contributed to understanding and advancing the ideas associated with it. In a couple of weeks, we'll launch our next series on the history of cartography that I'm tentatively titling Finding Our Way. It seems like a good way to complete the two aspects of cosmography, the cosmology we studied in Season 3, and that aspect of geography related to mapping our physical space. As we wrap up, let me once again say thanks to everyone for their kind words of condolence on the passing of my dad. It's been a tough couple of weeks, as you might imagine, but as they say, time heals. And so it is that I continue to move forward each day. Something made a whole lot easier knowing that I have so much support from the crew here. I appreciate all of you being on the voyage with me, and I hope you'll continue to engage on our various platforms, Facebook, Reddit, Twitter. Just search for The Scientific Odyssey, and you'll find us out there. Also, if you haven't done so and have a few minutes, we'd sure appreciate it if you could leave us a review on whatever service you use to listen to the podcast. It helps us get the word about what we're trying to do out and attract more crew members. Also, if you know someone who might enjoy the show, please share it with them across whatever platforms you're active on. Most important of those, of course, just being plain old word of mouth. Next time, we'll look at using dead reckoning to chart a path and map out a space. Until then, full sails on your journey.